beginning of our talk of factoring last week, I sort of had to give you a sales pitch on why we should care. Like, why do we factor in an algebra class? And the ultimate reason why we factor in an algebra class is it's going to let us do something that we weren't able to do with the techniques that we had at our disposal. We're going to be able, using factoring techniques, to solve new types of equations for which our usual solution strategy of isolate the variable, unwrap it using reversal order of operations, that usual strategy is not sufficient. And it's not sufficient because we have different powers of x in unlike terms in this expression. And since they're in unlike terms, we can't add or subtract them together to get them into one place so that we can target the x and we can unwrap it. Okay? So we need new strategies to solve equations like this one. And my sales pitch last week was that if we can factor the expression that's on the left-hand side of this equation, and the way that we did that was sort of using one of these lattices, these multiplication lattices, writing the x squared and the negative 14 on the inside, and then breaking apart the negative 14 in a few different ways until we found the right combination such that when I re-multiplied it back out, these middle terms added together to compensate for the minus 5 that we needed. If we know how to do that, then we're able to use this magic property of the real numbers called the zero factor property. If I have two terms multiplied by one another, I shouldn't say terms, if I have two factors, multiplied by one another and the product is equal to 0, then the zero factor property of the real numbers tells me I can break apart this equation into 2 bits. Because the only way to get 0 when we multiply two things is if one of those two things was originally 0 on its own. So the whole point of factoring is that if I have a factored expression on one side of an equation and 0 on the other side of that equation, I can break that complicated equation into 2 simpler pieces and then solve each of those 2 simpler equations to get my solutions. So that's the whole point of why we factor, is so that then we can do this, right? Factor, split, and then solve the simpler equations. So today's question is, how did I do this process? How did I know that x squared minus 5x minus 14 factors into x minus 7 times x plus 2? So let me just rewind our thought process one more time. And ask the question, all right, why, again, were negative 7 and positive 2 the right choices to give me negative 14? First of all, why are they the right numbers to put out here to give me negative 14 here in the middle? Why are 7 and negative 2 good for that? Seven and negative 2 are good because they multiply. When I multiply them together, I get negative 14. That's why in my multiplication lattice, if I put negative 7 here and positive 2 here, I get negative 14 in this square, right? Which is where I'm going to get this negative 14 if I were to multiply these back out using the lattice method. Okay? But 7 and negative 2 also have a second relationship that helps explain why they also account for this negative 5x. Okay? And that's what you were talking about a moment ago. Not only do these numbers multiply together to give me negative 14, what do they add together to give me? 7 plus, negative 7, I've got these backwards, don't I? Negative 7 and positive 2. Multiply together to give me negative 14, and they add together to give me negative 5. And that negative 5 is going to account for this negative 5 coefficient in front of the x. So our considerations in finding negative 7 and positive 2 for this factoring problem are that we're looking for a pair of numbers which multiply together to give me this constant, negative 14, but that same pair of numbers has to add together to give me that constant, the negative 5. Why? Because when I do out the rest of this multiplication lattice, that negative 7 and that positive 2 are going to account for the 2 terms here that have a single power of x in them. Negative 7 times x accounts for this negative 7x, and positive 2 times x is going to account for this 2x. And then when I add those two things together, combining like terms, the coefficients, negative 7 and positive 2, add together. And so I need them to add together to give me exactly this negative 5 that I was looking for. I call this the sum and product game. It's the game that we play anytime we try to factor one of these trinomial expressions. So we need a pair of numbers, whole numbers ideally. We generally don't play this game for fractions and stuff, though we could. It's just a lot harder to do. And we know what the sum that we need is, and we know what the product that we need is. We knew that we needed the product to be negative 14, and we knew that we needed the sum to be negative 5. But we always end up thinking about the product first because it gives us a much smaller search. There's a lot fewer pairs of numbers which multiply together to give me negative 14, fewer pairs of whole numbers which multiply together to give me negative 14, than there are pairs of whole numbers that add together to give me negative 5. If I think about the addition first, I'm going to have an infinitely long list of things I could choose. Right? I could choose negative 7 and positive 2, but I could also choose negative 8 and positive 3, negative 9 and positive 4, negative 10 and positive 5, negative 11 and positive 6, negative 12 and positive 7, negative 13 and positive 8, and so on and so on and so on. So if I think about the addition problem first, my list is going to be never-ending. That's why we think about the multiplication problem first, because that's a much shorter list. How do I multiply together and get 14? I could do a 14 and a 1, or I could do a 7 and a 2. And as far as whole numbers go, those are my only options. So that narrows down my universe, and then I can just try combinations. Try 14 and negative 1. Well, that multiplies correctly, but it doesn't add correctly. All right, what if I move the negative sign and do negative 14 and positive 1? That still multiplies correctly, but it doesn't add correctly, so I try something else. 7 and negative 2. Yeah, that multiplies correctly, but it doesn't add correctly. Move the negative sign. Negative 7, positive 2, there we go. So winning this sum and product game, finding this pair of numbers which has the product we need and the sum we need, that's how we fill out these constant terms when I factor a trinomial. And once I've done that, then the rest is sitting right there in front of me. So the next example, let's just look at this one. I'm going to have you do this one for, take a minute or so or two on your own, and then compare with somebody sitting next to you. If I want to factor t squared plus 19t plus 90, try and use the multiplication lattice approach that we used on the last problem to work this out. If I want my multiplication to come out to t squared plus 19t plus 90, and your job is to figure out how to get that, how to fill out this first row and this first column in a way that's going to make that happen. Think about the sum and the product game in working this out. So tell me how you approached this problem of factoring t squared plus 19t plus 90. What's the first thing you went searching for? So priority number one is that product. We want to find a pair of numbers which multiply together to give us 90. If we start with the sum, we'll be looking for a very long time. If we start with the product, it gives us a lot fewer to choose from. So two numbers which multiply together to give me 90. Now there's a lot of them to choose from. So which pair did you end up picking?
9 and 10.
9 and 10. And why was 9 and 10 a good choice?
It multiplies to 90 and I added it to 19.
Yeah, in addition to multiplying together to give us 90, it also added together to give us 19, which is the middle coefficient of this trinomial. So now that we know we have the right pair of numbers, let's look into the lattice and see how we use those numbers, right? The t squared in our product, we always end up sticking right here. And how do we factor the t squared? What times what? T times t. That one's one that we can just take to the bank. We always factor our squared variables in that way. But then, how do I fill in these other two entries here? 9 and 10. Those are my two numbers that win the sum and product game. And the reason for that is that we need, first of all, to account for this plus 90 in our product. And so 9 and 10 fit that bill just fine. So I'm going to write this as plus 9 plus 10. So this is plus 90 in here. But then, here's where the sum part in the sum and product game comes in. When I fill in these two diagonal squares in my lattice, that's where I end up with, in the upper right, plus 9t, and in the lower right, plus 10t, respectively, 9 times t and 10 times t. And sure enough, when I add those like terms together, I get my 19t. So now that we've won the sum and the product game, we've filled out our multiplication lattice completely, how do we actually write our final answer? How does t squared plus 19t plus 90 factor? T plus 9. Great. T plus 9 in parentheses, t plus 10 in parentheses. One of the greatest things, by the way, about factoring problems is you can always check your answer. How? If I was a little bit unsure about this answer, how could I check to make sure it was right? Just multiply it back out. Yeah, exactly. Multiply using whatever method you like for multiplication. If you decide to use the lattice multiplication method, well, our lattice already has your work written in for you. If we wanted to use a vertical method, we could. If we wanted to use a horizontal method, we could. But yeah, just multiply it back out. And if you got a correct factorization, then when you multiply it back out, you should end up back at t squared plus 19t plus 90. And if I ask WebWork, submit this answer, yeah, it likes it. T plus 9, t plus 10.